let's say this carbon number 2. So let's try take this carbon number to be big circle. So this carbon 2 be 0.8. So this carbon is the big circle, and this carbon number 2 is the dot inside. Okay, this carbon has 4 neighbors, 1, 2, 3, 4. Okay, now we're only showing only one neighbor, which is carbon number 2, which is the dots inside. Now we are left with these 3 neighbors, 1, 2, 3 hydrogens. Okay, so each of them will come off like this. Okay, so that's for this carbon number 1, which is a big circle. Okay. The smaller circle is inside here. It is joined to the big circle, which is carbon number 1. So this is right here. Okay. Now these 3 hydrogens right here. So we can show them coming off like this. So there's a Newman projection of it. Okay, so now that we know what are Newman projections, I want to do another example of conventional isomerism by using propane. Okay, this is C3H8 formula is okay. Now you can choose to use either this as a front carbon or back carbon. Either way, in every Newman projection you have to choose 2 carbons. Which carbon goes to the front and which carbon comes to the back. So I'm going to use this as a front carbon. Now this carbon has 3 hydrogens. Okay, so I'm going to write there. That means I will have to use this as a back carbon. Okay, now you see that there's an issue here. Okay, this carbon has 2 hydrogens, and then it has pointed to this whole group, which is CH3. So I'm going to show this CH. Right, this whole group is represented here. Then the two hydrogens comes here. Okay. So this is how the Newman projection of propane will look like. Okay. Alright, this is obviously target conformation. Alright, and then the eclipse will just look like this. Okay, this is an eclipse conformation where the substituents are bumping into each other. Okay. And this is high energy, this is lower energy. Conformational isomerism by using butane. So formula for butane is C4H10 and the open chain. Okay, so there are 4 carbons in the chain, and what I'm going to do is to choose 2 of the carbons that will give me more conformational isomers. So I'm going to choose the 2 inner carbons, this and this. Okay, now carbon number 1 I'm going to represent by a dot. This carbon has this hydrogen, and then this will be a whole group that's coming off of this carbon. So I'm going to draw them. Okay. Now this carbon is bonded to carbon number 2, which I'm going to represent by a circle behind carbon number 1. Okay, now this carbon number 2 has this whole group and this hydrogen and this hydrogen. Okay, and then let me draw the groups for the okay, so that is the first Newman projection representation for butane. Now what we do is we keep the front carbon, which I'm going to choose as carbon number 1, and then rotate the other carbon, which I'm going to choose as carbon number 2. So carbon number 1 is represented by the black color, and then carbon number 2 is the red color. So let's keep the black color constant and then rotate the red. Okay. And then we don't have to stop there, but we have to keep rotating. So this is now free, but the metal group is slightly getting closer to the other metal group. So another rotation. Okay, so this will give me all the conformations for butane, and to examine these 4 conformational isomers of butane, I have to look at how the groups are positioned away from each other. Over here, the bulky groups, which are the metal groups, are positioned like 180 degrees from each other. So this, of course, is a staggered conformation. And then this is eclipse, because the groups are eclipsing each other. Now this is staggered. And then this is eclipse. Awesome. Alright. Now this situation where the bulky groups are far apart from each other and directly opposite each other is called anti-conformation or staggered anti. It's called staggered anti because the bulky groups are 180 degrees apart from each other. Now this staggered conformation where the metal group is like 60 degrees apart from the other metal group has a name, is called gauge. G-A-U-C-H-E. That's a gauge conformation. And so the staggered ones are the most stable, and of course they are lower energy, because if you look at the eclipse, the groups are bumping into each other, so the energy is raised for the eclipse due to steric interactions between the groups. And this one here, you will see that the bulky groups are eclipsing each other. So this eclipse conformation will be the highest energy, because to have the largest steric interactions between these two bulky groups. This will also have a high energy, but not as high as this one. because over here hydrogen is eclipsing the metal groups, so there are still steric solars, but not as high as this one. Okay. Over here, the metal group is like 60 degrees apart from each other, so this is lower in energy compared to this and this. But this anti-circuit is the lowest because the bulky groups are 180 degrees away from each other, so there's least steric interactions between the bulky groups. The least or no steric interactions between the bulky groups. And yeah, usually the anti is lower in energy than the gauge, but in some strange cases, especially when hydrogen bonding is possible, they have found out that if there is hydrogen bonding involved in the gauge tend to have a lower energy than the anti, but those are very special circumstances. So usually the anti will have a lower energy than the gauge. So I'm going to draw the energy profile for this one. So this is the different conformations of butane, and I've labeled them A, B, C, and D. So I'm going to draw the energy profile. Lowest energy point is A, followed by C. The anti and the gauge are lower in energy, and then the two eclipse conformations, D higher in energy than B. So that's how the energy profile will look like.